Welcome back. In today's lecture I shall take up the subject of air conditioning, and we begin this subject with a topic called psychrometry. Okay. So, the specific objectives of this particular lecture are to discuss atmospheric air and its composition, estimation of moist air properties, important psychrometric properties and their relationship, psychrometric chart, thermodynamic wet bulb temperature, wet bulb thermometer and its use, and finally some empirical equations for vapor pressure. So, at the end of the lesson you should be able to define atmospheric air and its composition, explain methods of estimating properties of moist air, list important psychrometric properties and develop relationships between them, be able to find moist air properties from psychrometric equations and psychrometric charts, explain the concept of thermodynamic wet bulb temperature and its use, and explain the principle of wet bulb thermometer. So, we begin psychrometry with a small introduction. Atmospheric air makes up the environment in almost every type of air conditioning system. A thorough understanding of the properties of atmospheric air and the ability to analyze various processes involving air is fundamental to air conditioning design. Psychrometry is a study of the properties of mixtures of air and water vapor. This is a very important topic, and you must understand this topic thoroughly. So, first of all, let us look at atmospheric air. What is atmospheric air? Atmospheric air, as you know, is a mixture of many gases plus water vapor and a number of pollutants. Okay. That means you have a mixture of permanent gases, okay, like nitrogen, oxygen, argon, hydrogen, etc. There are almost about 15 gases. It is said that there are about 15 gases, okay. And you also have water vapor, and you also have dust particles, dirt particles, fumes, vapors, etc. Okay. So, all this taken together is what we call it as atmospheric air. The amount of water vapor and pollutants vary from place to place. However, concentration of water vapor and pollutants decrease with altitude, and about 10 km atmospheric air consists of only dry air. The pollutants have to be filtered out before processing the air. Hence, what we process is essentially a mixture of various gases that constitute dry air and water vapor. This mixture, that means the mixture of various permanent gases plus water vapor, is called as moist air. So, as I said, this entire thing is your atmospheric air, but in a typical air conditioning plant, what is done is, first of all, we filter this air. Okay, when you are filtering this air, you remove the dust particles, fumes, etc. Okay, so once you remove dust particles, fumes, etc., you are left with a mixture of permanent gases, and you call this portion, that means a mixture of permanent gases, as dry air, okay, plus water vapor. Okay, so this is what is actually processed or conditioned in an air conditioning plant. Okay, so this mixture of dry air plus water vapor is sent to an air conditioning plant for conditioning. Okay, so this mixture is called as moist air. The moist air can be thought of as a mixture of dry air and moisture. Moisture means water vapor. For all practical purposes, the composition of dry air can be considered as constant. It is observed that the composition of dry air remains almost constant wherever you go. That means it does not really vary with place to place or from altitude to altitude. Okay, so it remains more or less constant. Okay, so in 1949, a committee was formed to find or to fix the composition of this particular dry air for calculation purposes. Okay. So, as I said, the standard composition of dry air was fixed by the International Joint Committee on Psychrometric Data. Okay, so, what is the standard composition? The standard, according to this committee, this is the standard composition of dry air. Okay, so, it consists of oxygen, it consists of nitrogen, it consists of argon, and it consists of carbon dioxide. Of course, it also consists of many other gases such as hydrogen, helium, etc. But these gases, the concentration of these gases are very small. Okay, so as a result, it was decided by the committee that dry air means essentially these 4 components. Okay, and the properties of these 4 components are, as you know, oxygen molecular weight is 32. And its mole fraction in dry air is found to be 0.2095, and nitrogen molecular weight is 28.016 and its mole fraction is 0.7809. Okay, and argon molecular weight is 39.944, so mole fraction in dry air is 0.0093, and finally carbon dioxide molecular weight is 44.01 and its concentration or mole fraction is 0.0003 in dry air. Okay, so this is the mole fraction of various gases in dry air. Okay. So based on this composition, the molecular weight of dry air is found to be 28.966 and the gas constant R is 287.035 joule per kg Kelvin. It is important to remember these values because we will be using these values in calculations. Okay, so molecular weight of dry air is 28.966, gas constant of dry air is 287.035 joule per kg Kelvin. As I said, while the composition of dry air is constant, the amount of water vapor present in the air may vary from 0 to a maximum value. That means you can have a perfectly dry air, okay, that means there is no moisture at all, or you can also have a saturated air, that means air having a maximum amount of moisture, that means it can hold at a given pressure and temperature a certain maximum amount of moisture or water vapor. Okay. So this is the maximum that the air can contain. Okay. So in general, the amount of water vapor in air can vary between 0 to this maximum amount. Okay. When the moisture content is maximum, then the air is known as saturated air. The amount of saturated air is established by a neutral equilibrium between the moist air and the liquid or solid phases of water. Okay. So when you say that the air is saturated, that means essentially there is a neutral equilibrium between the moist air containing water vapor and a water liquid or solid. Okay, that means equilibrium between liquid water and moist air or between ice and moist air. For calculation purposes, we can take the molecular weight of water as 18.015 and the gas constant of water vapor as 461.52 joule per kg Kelvin. Now let us look at the estimation of properties of moist air. As I said, in most of the time in air conditioning you will be dealing with air. Okay, so in most of the calculations, for example, if you want to calculate what is the energy required for cooling air, what is the energy required for heating the air, you have to know the properties of air. Okay, what is the density of air, what is the specific volume, what is its specific heat, what is its enthalpy, right. So we have to find out various properties of air, right. Air is not a pure fluid, just now we have seen that it is a mixture of several gases plus water vapor. Okay. So by some means we must be able to find or estimate the properties of moisture for further calculations and design of air conditioning systems. Okay. It is difficult to estimate the exact property values of moist air as it is a mixture of several permanent gases and water vapor. If you want a 100% accurate or exact value, it is very difficult because it is a mixture of several gases and water vapor. Okay. However, moist air, it is found that moist air up to 3 atmosphere pressure obeys perfect gas laws with accuracy sufficient for engineering calculation. That means we assume that moist air behaves like an ideal gas or a perfect gas, so that you can apply the perfect gas laws, and it is observed that this does not really give rise to a huge error. For very high accuracy, of course, one has to consider the real gas behavior of moist air by considering interaction between molecules of various gases and water vapor. This requires application of principles of statistical mechanics. So for most of the time we need not really bother about the real gas behavior of various gases and water vapor. Okay, for our engineering purposes, even if you treat it as a mixture of ideal gases, that means you treat dry air as an ideal gas, and you also treat moisture, that means water vapor, also as an ideal gas, and take moist air as a mixture of ideal gases. Okay, this will give you reasonably good accurate values, but in some cases you may require much higher accuracy. Okay, in such cases you have to consider the actual real gas behavior of various gases. Okay, so when you consider the real gas behavior of various gases and all, you must consider the interaction between the molecules of various gases and between the molecules of the same gas. Okay, because in a real gas the molecular interaction is very much present. Okay, so one must consider these interactions, and one must evaluate the properties by taking all these interactions, by taking the volume of the volume occupied by the molecules, etc., into account. Okay, so this requires the application of the fundamental principles of statistical mechanics. Okay, so using this method, Goff and Grach have formulated tables for psychrometric properties. Okay, so these tables are based on the real gas behavior of moist air. Okay, so that will give you very good, very accurate properties. However, unfortunately, the Goff and Grach charts or tables are valid for 1 atmosphere barometric pressure. Okay, so if you want the psychrometric values at different barometric pressures, then again you have to do the calculations. Okay, so generally the calculations are found to be very complex. Okay, because of the number of gases involved. Okay, so what we will do is, and what is generally done is, assume that it is a mixture of ideal gases and apply the ideal gas laws and evaluate the properties. That is what is done in this lecture. Okay. So as I said, moist air is treated as a perfect gas mixture of dry air and water vapor. What is the justification? How do you justify this assumption that dry air behaves as an ideal gas and water vapor behaves as an ideal gas? This is justified because dry air may be assumed to be a perfect gas as its temperature is high relative to its saturation temperature. Okay, the saturation temperature of dry air is very low, so the actual temperature at which the air conditioning systems operate are much higher compared to the saturation temperature. Okay, so under these circumstances, dry air behaves more or less like an ideal gas. Okay, so the assumption is justified. When it comes to water vapor may be assumed to be a perfect gas because its pressure is low relative to its saturation pressure. Okay. So, normally in air the amount of water vapor that is there in air is very low. So, it exerts very low small partial pressure. Okay. So, this pressure is much lower than the saturation pressure. So, you can treat this as an ideal gas. And these assumptions result in accuracies that are sufficient for engineering calculations, and it is shown that the errors because of these assumptions is less than 0.7% for total pressure below 3 atmosphere. This is shown by Threlkeld. Okay, so since we are treating moist air as a mixture of perfect gases, that means moist air itself behaves as an ideal gas or a perfect gas. So we can apply the Gibbs Dalton law, and you know that Gibbs Dalton law for a mixture of perfect gases is given like this. According to Gibbs Dalton law, each perfect gas behaves as though it is occupying the whole volume, right, and there won't be any interaction between the molecules of different gases, right. So these are the assumptions. So since each gas is behaving as though it is occupying the whole volume, when you apply the ideal gas equation, the volume occupied by each gas is the total volume. Okay, and since you are talking about the equilibrium, the temperature of all the gases will be same. Okay. So then we get this equation. For example, let us say for gas 1, ideal gas equation is this: P1V is N1 RUT, where RU is the universal gas constant, N1 is the number of moles of P1, number of moles of 1, and T is the absolute temperature. Similarly, for gas 2, P2V is N2 RUT. Similarly, for gas 3, P3V is N3 RUT, like that. Okay. And when you apply this one and the conservation of number of molecules, that means N is N1 plus N2 plus N3, etc., you finally find that the total pressure, okay, PT is nothing but the summation of the individual pressures. That means PT is equal to P1 plus P2 plus P3, etc., okay, where P1, P2, P3, etc., are the partial pressures exerted by the individual gases. So when you apply this Gibbs Dalton law to moist air, in our case we have only two gases, that is dry air and water vapor. Okay, both, as I said, are assumed to behave as perfect gases. Okay, so if you apply this to moist air, you find that the total pressure or the barometric pressure PT is equal to Pa plus Pv, where Pa is the partial pressure of dry air and Pv is the partial pressure of water vapor. Now, let us look at important psychrometric properties. These psychrometric properties, what I shall do is define the psychrometric properties and give equations for the psychrometric properties, and these equations are derived based on the assumptions made earlier, that means based on the perfect gas model. Okay. The first and the most important property of course is the dry bulb temperature, in short form dBT, and it is denoted by small t, and it is, as you know, this is defined, it is the temperature of the moist air as measured by a standard thermometer or other temperature measuring instruments. So, actually dry bulb temperature is nothing but the temperature. Okay. So, we call it as we add the term dry bulb because we also have another temperature called as wet bulb temperature. Okay. So, to distinguish between these two, we call this temperature as dry bulb temperature. Okay. So, dry bulb temperature is nothing but the normal temperature measured by a standard or a normal temperature measuring instrument such as a thermometer. Okay. Next important property is the saturated vapor pressure, PSAT. This is the saturated partial pressure of water vapor at the dry bulb temperature. The saturated vapor pressures can be obtained from thermodynamic tables and charts. We have seen the thermodynamic tables and charts, and we have used these saturated vapor pressure of refrigerants while doing the calculations. So, for water also you can use similar tables and charts, and you can get the saturated vapor pressure value if you know the temperature. So, Asher suggested a regression equation for saturated vapor pressure of water, which is valid for 0 to 100 degrees centigrade. That means, if you have the thermodynamic tables or charts, then straight away you can get the values of saturated vapor pressure of water if you know the temperature. Okay. If you want to computerize this and if you want to do the calculations on the computer, then you need this in the form of an equation. Okay. So, Asher suggested a very accurate regression equation for the saturated vapor pressure of water. Okay. This equation is like this, ln Psat, okay, is equal to, you can see that C1 by T plus C2 plus C3 T plus C4 T square plus C5 T cube plus C6 natural log of T, where Psat is saturated vapor pressure in pascals. It is very important to note the units, okay, because you must use the same units to get the same values, okay, otherwise it will give wrong results. And T is the temperature, and it is in degrees Kelvin. Okay. So, this correlation is valid for these units, that means pressure in pascals, temperature in Kelvin. Okay. Of course, because you have to use these constant values. Okay. So, these constant values are valid for these units. Okay. And the values of constants C1 to C6 are given here, C1, C2, C3, C4, C5 and C6. So, if you substitute these values, then Psat is a function of temperature only. So, if you know the temperature, you can calculate the saturation pressure of water vapor, and as I said, this is valid for 0 degrees to 100 degrees centigrade. Next important property is relative humidity. It is symbol is phi, or sometimes RH is also used. It is defined as a ratio of the mole fraction of water vapor in moist air to mole fraction of water vapor in saturated air at the same temperature and pressure. Okay. So, it is a ratio, first of all, it is a ratio of mole fractions of what? Mole fractions of water vapor, that means actual mole fraction of water vapor, to mole fraction of water vapor in saturated air, okay, at the same temperature and pressure. Here the pressure means the barometric pressure, and temperature means the dry bulb temperature. Now, using a perfect gas equation, the mole fraction ratio can be replaced with partial pressure ratio. Okay. So, you can replace mole fraction by partial pressure. So, you can write finally relative humidity as partial pressure of water vapor divided by saturation pressure of pure water vapor at same temperature. That means PV divided by Psat. Psat can be obtained from the equation given just now or from the thermodynamic tables and charts. Normally, the relative humidity is expressed as a percentage, and if you say that phi is 100%, that means relative humidity is 100%, that means the air is saturated, because PV is equal to Psat. So, the air is saturated. Next important property is called as humidity ratio, and the symbol is capital W. It is defined as the mass of water vapor associated with each kilogram of dry air. Okay, so it is important to note that this is the mass of water vapor associated with each kilogram of dry air. And we can get an expression for this, assuming both water vapor and dry air to be perfect gases. The humidity ratio is given by this expression. Humidity ratio W is kg of water vapor divided by kg of dry air. Kg, that means the mass of water vapor, okay, MV divided by MA, and MV and MA are written in terms of pressures, volumes and temperature using the perfect gas equation, because we know that PV is MRT as far as the perfect gas equation is concerned. So, we replace the masses by these quantities. Okay. So, MV by MA, that means mass of water vapor by mass of dry air is written as PV into V by RVT divided by PA into V by RAT. Okay. Where PV and PA are the partial pressures of water vapor and dry air. RV and RA are the gas constants, not universal gas constants. These are the actual gas constants, and V's are the volumes and T's are the temperature. Since temperatures are same, volumes are same, these things get cancelled. Then we write PA in terms of total pressure PT and vapor pressure of water PV using the Dalton's law of partial pressures. Okay. So, PA is replaced by PT minus PV. So, finally, you find that W is equal to PV by RV divided by PT minus PV by RA, where RV and RA are the gas constants. And if you substitute the values of RV and RA, I have given the values of gas constant, you finally find that humidity ratio W is given by 0.622 PV by PT minus PV. Let me repeat once again, PV is the vapor pressure of water vapor and PT is the total pressure or the barometric pressure. So, you can see that the humidity ratio depends on the vapor pressure of water as well as the barometric pressure. Okay. Next property is called as the degree of saturation. The symbol is mu. This is defined as the ratio of humidity ratio W to the humidity ratio of a saturated mixer Ws at the same temperature and pressure. Okay. So, mu is given by W by Ws, where Ws is the saturated humidity ratio at the same dry bulb temperature and the total pressure. And of course, value of Ws can be obtained easily from barometric pressure and saturation pressure. Next comes the property called Dewpoint temperature or DPT. If let me explain this, if unsaturated moist air is cooled at constant pressure, then the temperature at which the moisture in the air begins to condense is known as dewpoint temperature of air. Okay. I am sure that you know what is the dewpoint temperature, but let me explain this with the help of a TS diagram. This is the TS diagram of water vapor. Okay. Let us say that this is your pressure, okay, total pressure. This is the saturated pressure at the dry bulb temperature T. Okay, so P is Psat. Now let us say that the water vapor exists at this point. Okay, that means it is in a superheated condition, right? So at this point, the temperature of the water vapor is same as the dry bulb temperature T, but its partial pressure is lower than the saturated pressure of water vapor. Okay, but you can see that this is the saturated pressure and this is the actual partial pressure. That means Psat is greater than PV. Now, if you cool this water vapor isobarically, that means along the constant pressure line. So, this is an isobar. Okay. So, if you cool the water vapor along the constant pressure line, its pressure reduces, its pressure remains constant, sorry, its temperature reduces, and you find that at a particular point the water vapor begins to condense. Okay. So, this is the point where beginning of condensation occurs. Okay. And you call this temperature at which the first drop of water forms is called as the dewpoint temperature. Okay. And actually, if you look at the TS diagram, what is dewpoint temperature? Dewpoint temperature is nothing but the saturated temperature corresponding to the partial pressure of water vapor. Okay. So, if you have the equation for partial pressure of water vapor, then you can easily solve that equation and find the dewpoint temperature. Okay. Of course, when the air is saturated, then dewpoint temperature is same as dry bulb temperature, because in that case your condition is somewhere here. Okay. So, an approximate but very useful equation for dew point temperature is given by this. dPT, the dew point temperature, is equal to 4030 into dBT plus 235 divided by 4030 minus dBT plus 235 into natural log of phi, where this phi is the relative humidity expressed as a fraction, okay, not as a percentage. And here dBT and dPT are in degrees centigrade. So, using this equation you can find out the dew point temperature if you know the dry bulb temperature and relative humidity. Next is the specific volume, small v. This, as you know, is defined as the number of cubic meters of moist air per kilogram of dry air. All these properties are moist air properties, okay, please keep that in mind. So, when I say specific volume, that means specific volume of moist air, right. So, from perfect gas equation, since the volumes occupied by the individual substances are the same, the specific volume is also equal to the number of cubic meters of dry air per kilogram of dry air, okay. Since each gas behaves as though it is occupying the whole volume, you can write the specific volume of moist air in terms of the volume and in terms of the mass of the dry air using this equation. Okay, this is the specific volume using the perfect gas equation for dry air. Pa into V is equal to Ra into T, where Pa is the partial pressure of dry air, V is the specific volume, and Ra is the gas constant and T is the dry bulb temperature, and Pa from Gibbs Dalton's law is nothing but Pt minus Pv. Okay. So, V is equal to Rat by Pt minus Pv, and the units are meter cube per kg dry air. Okay. Okay, before we go to the next properties, I just want to bring it to your notice that so far humidity ratio and specific volume, etc., these are all intensive properties. They are defined on basis of 1 kg of dry air. Okay, that means in the denominator you have kg of dry air. Okay. So, this may look a little surprising because we are talking about the properties of moist air. So, if it is a specific or intensive property, then it should have been the mass of dry air, that means kg of moist air, sorry, it should have been the kg of moist air, but we are writing this in terms of kg of dry air. What is the reason behind this? The reason is like this. Okay, so okay, so there is a small problem. Anyway, let me explain why we take the mass or the denominator as kg of dry air. That means why all the intensive properties are based on the mass of dry air. This is because of the fact that the amount of dry air in any air conditioning process always remains constant, whereas the amount of water vapor may get reduced or may increase. Okay. For example, if you are dehumidifying the moist air, then the amount of water vapor reduces. On the other hand, if you are humidifying the air, then the amount of water vapor increases. That means the mass of the moist air, total mass of the moist air may change, okay, during a given process, but the mass of the dry air always remains constant. Okay. So, if you write all the intensive properties in terms of the mass of dry air, then the calculations become very easy. Okay. So, this is the reason why all the intensive properties of moist air are based on the mass of dry air. Okay. Next important property for calculations is enthalpy. The enthalpy of moist air is the sum of the enthalpy of the dry air and the enthalpy of the water vapor, okay, because moist air consists of dry air as well as water vapor. So, the total enthalpy of the moist air is because of the contributions of the dry air part plus contribution of the moist air. Okay. And for enthalpies, we know that we have to define, you cannot have an absolute value of enthalpy. So, you have to have a reference values. So, here the references are like this. for dry air, the enthalpy of dry air is taken as 0 kilojoule per kg at 0 degree centigrade. This is the reference value for dry air. Whereas for water, the enthalpy of saturated liquid water is taken as 0 kilojoule per kg at 0 degree centigrade. So, these are the reference enthalpy values based on which we define the enthalpy of moist air. So, the enthalpy of moist air is given by HA plus W into Hg. Okay. So, where HA, this is an intensive property. So, the unit is kilojoule per kg of dry air, right. So, everything is in terms of kg of dry air. So, HA is nothing but the contribution of the dry air part, and it is nothing but the enthalpy of the dry air, okay. And W into Hg is the contribution of the water vapor. In this, Hg is the enthalpy of the water vapor and W is the humidity ratio, okay. So, the first term takes care of the contribution of the dry air, and the second term takes care of the contribution of water vapor, okay. And if you assume or if you use an average value of specific heat Cp, and if you take these reference values, then you can write HA plus WHG in terms of specific heats and temperatures like this. That means finally enthalpy of moist air is written as Cp into T, where Cp is the specific heat of the dry air, specific heat at constant pressure of the dry air, T is the dry bulb temperature, W is the humidity ratio, HFG is the latent heat of vaporization of water, CPW is the specific heat of water vapor at constant pressure, and T is the dry bulb temperature, okay. And HFG is actually the latent heat of vaporization at 0 degree centigrade, because the difference is at 0 degree centigrade. So, you can take an approximate value of 2501 kilojoule per kg, okay. So, remember that when you are writing these enthalpies in terms of specific heat, that means when you are writing the delta H as Cp into delta T, that means we are using average value of specific heat, okay. So, substituting approximate values of Cp, Cpw and HFG, we obtain this expression. H is 1.005 T plus W into 2501 plus 1.88 T, okay. This is obtained by taking a specific heat value of 1.005 kilojoule per kg Kelvin for dry air, okay. So, this is the Cp of dry air, and this is the latent heat of vaporization at 0 degree centigrade, and this is the Cp of water vapor, okay. So, if you remember these things, these simple equations, then it is very easy to calculate various properties, okay. For example, enthalpies and all, if you know other properties, right. Next property is the humid specific heat, that is nothing but the specific heat of the moist air. The symbol is C subscript Pm. From the equation of enthalpy of moist air, the humid specific heat of moist air can be written as Cpm is Cp plus W into Cpw, where Cp is the specific heat of the dry air, W is the humidity ratio, and Cpw is the specific heat of the water vapor at constant pressure. And of course, the units of Cpm are in kilojoule per kg dry air per Kelvin, okay. And for all practical purposes, you can take you can use a mean value of humidity ratio, and you can take the value of Cpm as 1.0216 kilojoule per kg dry air Kelvin, okay. Next, let us look at psychrometric chart. What is a psychrometric chart? So far we have seen the psychrometric equations, then let us look at the psychrometric chart. A psychrometric chart graphically represents the thermodynamic properties of moist air. It is nothing but a graphical representation of moist air. Standard psychrometric charts are bounded by the dry bulb temperature line on the abscissa and the vapor pressure or humidity ratio as an ordinate. And the left hand side of the psychrometric chart is bounded by the saturation line. Okay, let me show the psychrometric chart now. Okay. So, this is the skeleton of a psychrometric chart. As I said, you have the dry bulb temperature dBT on the x axis, and here you have the humidity ratio W on the y axis. Of course, you can also have in place of W, you can also have vapor pressure of water, okay, because these are related, okay. One very important thing is that in order to find the way, we will come to that. In order to fix the state of moisture, we need to know 3 independent properties. Okay, so that means the degrees of freedom are 3, because we are talking about a binary mixer. Okay, but the psychrometric chart is a 2-dimensional representation of the properties. So how is it possible? This is made possible by giving the psychrometric charts for standard barometric pressures. Okay, that is how a 3-dimensional figure has been reduced to a 2-dimensional chart. Okay, that means any psychrometric chart is valid for that particular barometric pressure, and if you look at any psychrometric chart, they always mention the barometric pressure at which the chart has been obtained. Okay, so they always say that P values, for example, if it is standard atmosphere, they say P is 101.325 kilopascal. Okay, that means it is 1 atmospheric pressure, like that. Psychrometric charts are of course available for different barometric pressures. Okay, so you must whenever you are using psychrometric chart, you have to be careful, and first of all you have to see for what barometric pressure that particular chart is valid. Okay, so you cannot use the same chart at all altitudes. Okay, now coming back to the psychrometric chart. A psychrometric chart, as I said, is a graphical representation of psychrometric properties, and using the psychrometric chart you can find the properties of all psychrometric properties. Okay, and this, as I said, is a saturation curve, the left hand side. Saturation curve means relative humidity is 100%, and on the same chart you find constant relative humidity lines. These are the constant relative humidity lines. Okay, for example, this could be the 75% relative humidity line, this could be 50% relative humidity line, this could be 25% relative humidity line, like that. Okay, so that is, those are the constant relative humidity lines. Of course, since the dry bulb temperature is the x axis and humidity ratio is the y axis, obviously these lines are the constant dry bulb temperature lines. Okay, they are not exactly vertical, but for all practical purposes they are almost vertical. Okay, so the vertical lines are dry bulb temperature. All the horizontal lines, these lines are the constant humidity ratio lines. Okay, and as I said, these curved lines are your relative humidity lines, and these dashed lines, okay, these are the specific volume lines. Okay, all these dashed lines are specific volume lines, and finally you have these thick inclined lines. Okay, all these thick inclined lines are constant enthalpy lines. Okay, so you can see that all the required properties are specified on the psychrometric chart. Okay, so if you know any two properties, any two psychrometric properties, you can find the rest of the properties. For example, if you know the dry bulb temperature and relative humidity, let us say this is your dry bulb temperature. This is your dry bulb temperature, let us say, and this is your relative humidity. Okay, that means this is the state of the air, this point, and then you can find out the humidity ratio like this, you can find out the specific volume like this, you can find out the enthalpy value by reading this line, like that. Okay, so remember again that this is for a given pressure. Okay, so you, if you need to know the properties, you need to know the barometric pressure plus any other two properties. Okay, so once you have these three properties, you can find the rest of the properties using a psychrometric chart. Okay. This actually shows, this picture is not very clear, but this is the psychrometric chart given by ASHRAE, and ASHRAE has provided psychrometric charts which can be used for different elevations, and this particular chart is valid for 1 atmospheric pressure. Okay, barometric pressure. They have also given similar charts for different elevations, for example for 1500 meter elevation, for 1000 meter elevation, like that. That means for different charts for different elevations and different conditions. And again, as I said, you have the dry bulb temperature here, and you have the saturation humidity ratio as a ordinate, and all these curved lines, okay, are your relative humidity lines, and the slant lines are specific volume lines and enthalpy lines. Okay. So, using the psychrometric relations, one can construct a psychrometric chart. This is a usefulness of having the psychrometric relations. You can construct your own psychrometric chart using the simple relations. Okay, this is very easy. All that you have to do is you have to take the dry bulb temperature on the x axis and take the humidity ratio on the y axis, and you have to have the steam table or so steam charts or the regression equation for saturation pressure of water vapor. if you have these three, then using the psychrometric relations you can construct the psychrometric chart. The advantage of constructing your own psychrometric chart is you can construct the psychrometric chart for any barometric pressure. Okay, there is no limitation, but of course remember that all these relations are based on the assumptions of ideal gases. Okay. Psychrometric charts are extremely useful in the analysis of air conditioning systems. We will be using these charts again and again for showing the psychrometric processor, for estimating the psychrometric properties, etc. Now, measurement of psychrometric properties. Based on Gibbs phase rule, the thermodynamic state for moist air is uniquely fixed if the barometric pressure and two other independent properties are known. As I have already mentioned, if you apply the Gibbs phase rule, that is number of P plus V, C plus 2, where P is the number of phases present and V is the degrees of freedom and C is the number of components, you find that the degrees of freedom or number of independent components to be specified are 3 for moist air. Okay, when you treat it as a mixture of two components, right. So, minimum number of 3 parameters have to be, 3 independent parameters have to be specified to fix the state of moist air. Okay. So, what are those 3 parameters? Unless you fix these 3, unless you specify these 3, you cannot find the properties of moist air. Okay. Normally a barometric pressure is specified because we know the barometric pressure. So, at a given barometric pressure, the state of moist air can be determined by measuring any 2 independent properties. Okay, so, given the barometric pressure, we need still 2 more properties. One of them could be the dry bulb temperature, as the measurement of temperature is fairly simple and accurate. Okay. So, if you need 3 independent properties, one of them is barometric pressure because it is known to us. Okay. So, it is easy to fix it. Other one could be dry bulb temperature. Right. What is the third property? Okay, what is the third property which can be specified and which can be measured easily, so that you can fix the state of air. Okay. Third property could be, theoretically third property could be anything. For example, the third property could be relative humidity, third property could be humidity ratio, it could be for example enthalpy. Of course, enthalpy cannot be measured, so there is no point in taking that as an independent variable, but theoretically speaking it can be any intensive property, right. But there are some problems with some of the independent intensive properties. For example, if you want to specify humidity ratio as an independent property, it is not very convenient because accurate measurement of humidity ratio is very difficult in practice. Since measurement of temperature is easier, it would be convenient if the other independent parameter is also a temperature. So, one of the independent parameters is dry bulb temperature. So, if the other independent parameter is also a temperature, then it will be very convenient to us because it can be measured very easily, right. So, temperature measurements are easier, right. But could it be the dew point temperature? Accurate measurement of dew point temperature is difficult. So, even though dew point temperature is also a temperature, taking that as an independent parameter is difficult in practice because measurement of dew point temperature is very difficult, okay, just like humidity ratio. Okay. Hence, a new independent temperature parameter, the wet bulb temperature, is conceptualized. Okay. Because of this difficulty, that means because of the difficulty of measuring other properties such as the humidity ratio or relative humidity or dew point temperature, people have come out with a new concept of wet bulb temperature. Okay. So, this concept is very useful because we shall see that measurement of wet bulb temperature is relatively easy compared to dew point temperature. Okay. So, compared to, as I said, compared to dew point temperature, it is easier to measure the wet bulb temperature of moist air. To understand the concept of wet bulb temperature, it is essential to understand the process of combined heat and mass transfer. So, we have to have combined heat and mass transfer. When we discuss combined heat and mass transfer with reference to a mixture of air and water vapor, then we have to talk about a law called as straight line law. What is the straight line law? The straight line law says that when air is transferring heat and mass, here mass means water vapor, to or from a wetted surface, the condition of air shown in a psychrometric chart drives towards the saturation line at the temperature of the wetted surface. Okay. So, this is the straight line law. Let me explain this. Let us say that we have moist air For the time being, let us assume that this is unsaturated, okay, that means its relative humidity is less than 100%. And let us say that we have a moist surface, okay, this is a wet surface. That means on this surface we have a layer of water, let us say, okay, and for argument's sake let us assume that this water is at a different temperature compared to this air, or for the time being let us say that if this water temperature is Tw, Tw is less than the air temperature T1, okay. And on the psychrometric chart, let us say this is the condition of the air at this point at point 1, it is at some dry bulb temperature T1, okay, and at some humidity ratio W1. So, air at this condition is coming in contact with a wet surface at temperature which is at temperature Tw. When you have a wet surface at temperature Tw, a concentration boundary layer develops near the wet surface, and air in the immediate vicinity of the wet surface will be saturated. That means in the immediate vicinity of this wet layer you have a saturated water vapor layer, and since this temperature is also same as Tw, the condition of that layer will be represented by this point, okay. So, this is the condition of the saturated water vapor next to the wet layer, okay. So, air is coming in contact with this. Now, you can see that there is a temperature difference between this saturated air and this air, okay, that is that this temperature difference is there. Similarly, there is a vapor pressure difference or humidity ratio difference, okay. Humidity ratio difference means vapor pressure difference is also there, okay. Since the vapor pressure and temperature of this air are greater than the water vapor, saturated water vapor, heat transfer will take place, sensible heat transfer will take place from air to the water, and latent heat transfer will also take place from air to the water. That means this warm air, when it comes in contact with a cold wetted surface, it gets cooled and dehumidified, okay. So, what you are getting outside, that means what you get at point 2 is a cold and dehumidified air. Now, the question is what will be the condition of this air, okay. How do you determine this condition of this air, or where does this point lie, okay. This is where the straight line law is useful, okay. The straight line law says that the condition of this point, okay, lies on a straight line joining these 2 points, okay. That means joining the points of the saturated water vapor condition and the inlet air condition, okay. The straight line joining these 2 points is this, and that means this exit condition must lie on this straight line, okay, for example on this point. So, this is what is known as straight line law. So, straight line law is applicable to air water mixers. As for these mixers, the Lewis number is close to 1. Now, let us look at another concept, that is thermodynamic wet bulb temperature and the process of adiabatic saturation. Adiabatic saturation temperature is defined as that temperature at which water by evaporating into air can bring the air to saturation at the same temperature adiabatically, okay. An adiabatic saturator is a device using which one can measure theoretically the adiabatic saturation temperature of air, okay. Let me describe this. Okay. So, this is an adiabatic schematic of a adiabatic saturator. So, what we have is an infinitely long duct, let us say, okay, and this duct is perfectly insulated, right, and it consists of water, okay. Now, moist air at this condition, dry bulb temperature T1, humidity ratio W1 and total pressure P flows through this insulated infinitely long duct, okay, and as it flows through this, it comes in contact with this water, okay. So, as a result you have sensible as well as latent heat transfers take place, sensible heat transfer plus latent heat transfer takes place, okay. And if you are measuring, let us say using this thermometer, we are measuring the temperature of this water, and if this duct is infinitely long and if the system reaches a steady state, you find that at steady state for an infinitely long duct, the exit temperature of the moist air will be same as the temperature indicated by this thermometer. That means the exit temperature of water moist air will be same as the steady state temperature of the water. Okay, both will indicate the same temperature. Of course, during this process water vapor evaporates. To take care of that, we have to continuously supply some makeup water. Okay, so this kind of a device is called as an adiabatic saturator. At steady state condition, the temperature indicated by the thermometer immersed in this sump is the thermodynamic wet bulb temperature. Okay, that means thermodynamic wet bulb temperature is nothing but the temperature indicated by a thermometer which measures the water kept in the sump of this infinitely long duct. Okay. Now, certain combinations of air conditions will result in a given sump temperature. Okay. From energy balance for adiabatic saturator based on 1 kg per second of dry air flow rate, we can derive this energy balance equation. Okay. So, if you take this as a control volume, and apply energy balance equation, you find that energy coming in is energy going out. Energy coming in, everything is on base of 1 kg of dry air, so energy coming in is nothing but H1 plus this energy, this is nothing but W2 minus W1 into HF, where W2 minus W1 is nothing but the amount of water evaporated in the adiabatic saturated, and HF is the saturated liquid water enthalpy at this temperature T2. Okay, so this is the energy entering, and what is the energy leaving? Energy leaving is nothing but H2. Okay. So, assuming the moist air specific heat CPM to be constant, energy balance equation can be written in this form. Okay, so we can write the energy balance equation like this, where T2 is the exit or thermodynamic wet bulb temperature, T1 is the inlet dry bulb temperature, HFG2 is the latent heat of vaporization at temperature T2, CPM is the moist specific heat, W2 and W1 are the exit and inlet humidity ratios. Since the outlet condition is saturated, the exit properties W2, HFG2 are functions of temperature T2 only. Okay, because the outlet condition is saturated. Of course, this is at a given barometric pressure. Hence, from the energy balance, T2 is equal to T1 minus HFG2 by CPM into W2 minus W1. Okay, so what I am saying here is W2 this is a function of temperature only, and this is also a function of temperature T2 only. Okay. So, ultimately from this this implies that T2, that means the exit temperature, is a function of T1 and W1 only, right, because you have temperature T2 on this side. Apart from T2 you have only T1 and W1, that means T2 is a function of T1 and W1. T1 and W1 are the properties of the inlet state. So, finally what we are saying is the temperature measured by the thermometer is nothing but a function of inlet state. Okay. In other words, the thermodynamic wet bulb temperature T2 is a property of moist air. Thus, measuring dry bulb temperature, wet bulb temperature and barometric pressure, one can fix the state of air and find all the required properties of moist air. Okay. So, what we are saying finally is that if you can have an adiabatic saturator, and if you can measure the temperature of the water in the adiabatic saturator at steady state, then you have another property of moist air. Okay. So, one property is dry bulb temperature, the other property is thermodynamic wet bulb temperature. Okay. So, from these two temperature values and the barometric pressure, you can find out the rest of the psychrometric properties. Okay. Now, T2 is a function of T1 and W1. This is not a unique function, because in the sense that there can be several combinations of T1 and W1 which can result in the same sump temperature in the adiabatic saturator. Okay, that means several inlet conditions can result in the same sump temperature. That means they all have same thermodynamic wet bulb temperature. Thus, all inlet conditions that result in the same sump temperature have the same wet bulb temperature. A line passing through all these points is a constant wet bulb temperature line, because all these points have the same wet bulb temperature line. Obviously, line passing through all these points is a constant wet bulb temperature line. The line 1, 2 is a straight line as per the straight line law and represents the path of the air as it passes through the adiabatic saturator. Okay, that means let us say that this is our inlet condition to the adiabatic saturator, and the outlet condition is a saturated air, so it lies on the saturated line. Okay, and the process follows the straight line joining 1 to 2 according to the straight line law. That means the line joining 1 to 2 is a constant wet bulb temperature line. Okay, whereas this line what is shown here is a constant enthalpy line. So, there is a difference between constant enthalpy line and constant wet bulb line, and what is that difference? From energy balance you can show that that difference is nothing but W2 minus W1 into HF. The thermodynamic wet bulb temperature will be less than the entering air dry bulb temperature, but greater than the dew point temperature obviously. At dry bulb temperature, wet bulb temperature and dew point temperature will be same when the air is saturated. Normally lines of constant wet bulb temperature are shown on the psychrometric chart. So, psychrometric chart also has lines of constant wet bulb temperature. The difference between actual enthalpy and the enthalpy obtained by following constant wet bulb temperature is equal to W2 minus W1 into HF. This is from the energy balance for the adiabatic saturator. Okay. Now, let us quickly look at what is known as the wet bulb thermometer. In practice, it is not convenient to measure the wet bulb temperature using an adiabatic saturator. Instead, a thermometer with a wetted wick is used to measure the wet bulb temperature. Okay. We cannot find the, in practice you cannot have a infinitely long and perfectly insulated duct and wait for its steady state and measure its temperature. Okay, it is not convenient, it is not practically feasible. Okay, so in practice what we use is what is known as a wet bulb thermometer. Okay, what is a wet bulb thermometer? A wet bulb thermometer is nothing but an ordinary thermometer, but its bulb, sensing bulb is covered with a wet wick. Okay, so this is covered with wet wick, that means you have a moist wick. Okay, and air flows over this one, right, and the temperature measured by this is your, we call it as wet bulb temperature or WBT. Okay, and if you are applying the straight line law, you find that if this is the inlet condition to the wet bulb thermometer, and if this is the temperature of the moisture on the bulb, okay, then you find that the outlet condition lies somewhere here. Okay, and it is called as a Lewis number. So, when Lewis number becomes 1, then the temperature measured by a wet bulb thermometer is same as the thermodynamic wet bulb temperature. Okay. So, this is the principle. Of course, it should be noted that unlike thermodynamic wet bulb temperature, the wet bulb temperature of wet bulb thermometer is not a thermodynamic property, as it depends upon the rate of heat and mass transfer between the wick and air. So, precautions have to be taken while measuring the WBT using wet bulb thermometer. For example, when you are using the wet bulb thermometer, you should make sure that the wick is always clean and wet, air around the bulb should not be stagnant, water used should have a temperature closer to wet bulb temperature, or sufficient time must be allowed for steady state, and radiation shields must be required to reduce errors due to radiation, etc. Okay. So, for air water mixers, we assume that the temperature measured by wet bulb thermometer is equal to the thermodynamic wet bulb temperature, but this may not be valid for other gas vapor mixers. Okay, there can be appreciable differences when you are talking about other gas vapor mixers. And an instrument used for measuring the psychrometric state of air is called as a psychrometer. Okay, there are different types of psychrometers. So, at this point I stop this lecture. Okay, thank you.